Hello again, and welcome to Advanced Physics for High School Students. This is Lesson 34, and it is entitled Graphical Analysis of Linear Motion. We've already been doing a lot with graphical analysis of motion. We've looked at position versus time graphs, velocity versus time graphs, and acceleration versus time graphs. In a moment, we're going to summarize what points that we have seen so far. The main thing that I want to try to emphasize in this lesson is creating one type of graph when you're given another type of graph. Now, your textbook does a pretty good job of summarizing position versus time and velocity versus time graphs. More than likely, you're only going to see these sorts of graphs dealing with constant acceleration. So I'm going to jot down the same things that your authors do on page 279 of your textbook for position versus time graphs, and then also on page 283 of your textbook for velocity versus time graphs. Starting with the position versus time graphs, there are four major points. First, a linear section of a position versus time graph indicates constant velocity. The second point, if there is a curved section of an x versus t graph, then that means the object's accelerating. If the curve is concave up, in other words, it holds water, if you think about gravity in a bowl, then we would say that that's positive acceleration. If it is concave down or spills water, if you think about it, a bowl trying to hold water, then we say the acceleration is negative. Third point, if I have a point on the x versus t graph and I sketch a tangent line at that point and I find the slope of that tangent line, that's going to tell me what the instantaneous velocity is at that point. And then finally, wherever the graph begins at t equals 0, that vertical intercept, wherever it hits that position versus time graph, is going to be the initial position, x0. Now we move on to velocity versus time graphs, and we'll do a similar sort of summary for them. The first one is that if I have a horizontal segment of a v versus t graph, that means constant velocity or zero acceleration. Second point, a linear section of a v versus t graph indicates constant acceleration. If it has a positive slope, that'll be a positive acceleration. If it's a negative slope, it'll be a negative acceleration. Third point, if I sketch a tangent line at a point of a v versus t graph, then the slope of that tangent line gives me the instantaneous acceleration at that point in time. Fourth point, if I find the area bounded by a v versus t graph and the time axis, then that's going to give me displacement. Those displacements could be positive if the v versus t graph is above the time axis. It could be negative if it's below the time axis. And then finally, wherever the graph begins at t equals 0, that is going to be the initial velocity of the system at that point. I'm not going to sketch graphs for these things. Your authors do that in the textbook, and I would encourage you, if you're rusty on that, to go back and take a look. But one thing I want to point out that your authors don't do explicitly is that if you're dealing with constant acceleration, then these graphs are connected to the equations of motion for constant acceleration. I'm going to write those equations of motion just here to the right to remind us of that and to realize that we have those tools that we can use to help us if we need to analyze the motion. Of these three equations of motion, the first two are probably going to be the ones that are most connected with these position and velocity versus time graphs, and that's because time shows itself explicitly in these equations. Now, I want to work one example, and it's an example that your authors have in the textbook, and I have modified it slightly. The graph shown below shows the velocity of a truck plotted as a function of time. Part A. Describe the motion of the truck during the time period from t equals 0 to t equals 12 seconds. B. How far did the truck travel in the first 9 seconds? C. And now here's where the modifications come. Sketch the position versus time graph for the truck for the first 12 seconds, assuming its initial position was at 0. Your authors actually ask you to sketch it for the first 9 seconds. I've extended it to 12 seconds. D, this is a new part as well. Sketch the acceleration versus time graph for the first 12 seconds. Okay, well, let's solve this problem. First of all, we need to describe what the motion of the truck is. Let's do that over here at the side. I'm going to break the graph into 3 different segments, from 0 to 5 seconds, from 5 to 9 seconds, and from 9 to 12 seconds. I'm going to call those segments A, B, and C. So let's talk qualitatively about the motion of the vehicle. In segment A, the velocity starts at 20 meters per second. At 1 second, it's still traveling at 20 meters per second. At 2 seconds, it's still at 20. I have a horizontal line. This is a velocity versus time graph, and that means that the velocity from 0 to 5 seconds is constant. It's at 20 meters per second. The object's moving at constant velocity. There is no acceleration. Now, segment B, from t equals 5 seconds to t equals 9 seconds. The truck starts at 20 meters per second. It ends up going 45 meters per second. So the truck is changing its speed. It's actually speeding up. And as it's speeding up, then it is going to cover more and more distance per time. But for our purposes right now, we're just concentrating on the velocity. It is picking up speed. It has positive acceleration. And in a moment, we're going to calculate what that acceleration is. Then finally, segment C. The truck at 9 seconds is moving at 45 meters per second. Now, over the next 3 seconds, the truck slows down. And it slows down at a constant rate until it reaches 0 meters per second at 12 seconds. So over that 3-second time interval, it is slowing down from 45 meters per second to 0 meters per second. It is got negative acceleration during that time. Part B asks us to calculate how far the truck moves in the first 9 seconds. And I'll remind you that we can find the displacement by looking at the area that's bounded by this velocity curve. I could draw myself a rectangle whose top starts at plus 20 meters per second and goes all the way over for 9 seconds. So basically, this rectangle that I'm filling in right now is going to be part of that area. And then sitting on top of that rectangle, I have a triangle. And this triangle that's on top has an area of 1/2 of the base times the height. So if I add those two areas together, that's going to tell me what the displacement is. So let's figure out the areas of those two geometric figures. So the displacement is going to be the area bounded by the v versus t curve and the time axis. I've got 2 pieces. I've got this blue piece and I've got this yellow piece. So I've got the area of a rectangle plus the area of a triangle. The area of a rectangle is the base times the height. In this case, the base is 9 seconds long and the height is 20 meters per second. For the triangle, I have a base that's 1, 2, 3, 4 seconds long and a height that starts at 20 and goes up to 45, so the height is 25 meters per second. I find that during the first 9 seconds, the object travels 230 meters. That's part B. Now in part C, this is the part that I really want to focus on that I think is fairly new in this lesson. We want to take this velocity versus time graph and from it to sketch the position versus time graph. And we're going to do it for the first 12 seconds. All right, during the first 5 seconds, the object travels from its initial position of 0, which I'm going to mark right here, up to 100 meters. I know it travels 100 meters because the area of this segment here in the velocity versus time graph is the base times the height. The base is 5 seconds, the height is 20 meters per second. 5 seconds times 20 meters per second is 100 meters. Now we need to figure out how far that the object travels between 5 seconds and 9 seconds. Well, a piece of that is going to be this rectangle that's underneath there. It is 4 seconds long, 6, 7, 8, 9 times 20 meters per second wide, so that is now 80 meters that it's going to travel as a result of that, plus the 50 meters of the yellow rectangle, the yellow triangle that's on top of it here. This triangle right there is another 50 meters. So 80 meters and 50 meters is an additional 130 meters. So if I am starting at 100 meters and I travel up to another 130 meters, that's going to be at 230 meters when I get to the 9-second point. Now it's not going to do this in a linear way, it's going to do it kind of in a parabolic way. Parabolic because I've got constant acceleration, and so I'm going to have a curved line. I'm going to try to sketch that in a curved way. Now, what about from 9 seconds to 12 seconds? Now it's true that the object's slowing down, but it's still traveling in the same direction that it was going initially. It started at 45 meters per second, and it's going to end at 0 meters per second. So it's like the guy has slammed on the brakes, and he's slowing this train down, and I need to find the area that's underneath that curve right there. Well, the area is going to be 1/2 of the base times the height. So the area underneath that is 1/2 of the base, which is 123 seconds, times the height, which is 45 meters per second. And so I need to figure out what that distance is. I find that the thing travels another 67.5 meters in the positive direction. So here I am at 200 meters, 230 meters at the end of the 9th second, and I'm going to travel another 67.5 meters. So 230 and 67.5 is going to be 297.5 meters, just under 300 meters. The object is slowing down, so this would be a concave down curve. So between 9 and 12 seconds, the object is slowing down. It has negative acceleration. Between 5 and 9 seconds, the object is speeding up. So that's a concave up position versus time graph. And then during the first 5 seconds, it is a linear position versus time graph. So there is no acceleration during that segment. All right, now here is the last part. This is a part that I've added. It says sketch the acceleration versus time graph for the first 12 seconds. First of all, let's recognize that I still have 3 segments, between 0 and 5 seconds, between 5 and 9 seconds, and between 9 and 12 seconds. During the first 5 seconds, the acceleration is 0 because there's no change in velocity. And so I'm going to sketch that graph between 0 and 5 seconds on the acceleration versus time graph. Now let's go from 5 to 9 seconds. What's the acceleration? Well, the acceleration is the change in velocity with respect to time. The final velocity up here is 45 meters per second at a time of 9 seconds. Over here, the velocity is 20 meters per second at a time of 5 seconds. So the change in the velocity is plus 45 minus 20, which is 25 meters per second, divided by the time it takes to do that, 1, 2, 3, 4 seconds. So I can calculate what the acceleration of that segment of the graph is. I get that the acceleration is 6.25 meters per second squared, and it's a positive number. So at t equals 5 seconds, I suddenly jump up to 6.25 meters per second squared, and I do that until I get up to 9 seconds. So this is going to be a horizontal line between those 2 points. Now, I get to the 3rd segment of the graph. The object slows down. It starts at 45 meters per second, and it ends at 0 meters per second, and it takes a time of 3 seconds to do that. So the acceleration during that segment is the change in velocity divided by the time interval. But now I change by an amount of negative 45 meters per second. In a 3-second time interval, the acceleration is negative 15 meters per second squared. And so suddenly at 9 seconds, I'm going to go at this negative 15 meters per second squared, and that's going to happen for the remainder of the graph. Now you've been solving these graphical analysis motion graphs for some time now, and so I'm not going to belabor the point. But the idea is you can break the graphs into segments, usually constant acceleration segments, and analyze the motion piecewise, and then from these graphs you need to be able to sketch other graphs. We started with velocity versus time graphs and sketched a position versus time, and then sketched an acceleration versus time, but you need to be able to go between all of those. So that's it.